So it's a great honor and pleasure to be here. Actually, I used to spend a lot of time here about 35 years ago working with Nati when he was a postdoc here, actually. I was over at the university, and I haven't been back here in decades. And actually, I'm seeing a lot of people I haven't seen in decades, so it's really fun to reconnect with all these people and places. So at the time, I was working with Nati and Mike Dine on a problem involving supersymmetry. And I guess we did such a thorough job on this problem, including Nati's work afterwards, that I haven't actually worked on supersymmetry after that for the next 35 years or something. But coincidentally, I got back into supersymmetry in the last year or two. So it seemed like a perfect topic to talk about at this meeting. So this is collaborative work with Armin Ramani, who was a postdoc at UBC. He's actually just moved to a faculty position at Western Washington University. And my colleague Marcel Franz and a graduate student, Xiaoyu Zhu. Okay, so what is the model I'm talking about? It looks like an incredibly simple model. In fact, when we wrote down this model, we sort of asked ourselves, why didn't somebody solve this model a long time ago? So it's just a model, it's the simplest model you could write down in one dimension involving Majorana fermions. So gamma J's are Hermitian fermion operators, any commutation relations. And we had the shortest range possible interaction you could actually add. So because the square of one of these Majoranas is 1, you have to have 4 lattice sites at least to have an interaction. So this was a model we considered. Unlike the ordinary complex fermion version of this model, there's no conserved particle number, but there are some important discrete symmetries. As far as we know, it's not beta ansatz integrable. Maybe I'm wrong. But the model can be studied using field theory methods and numerical techniques, density matrix normalization groups. So I'll be telling you about both types of results. So what is the experimental motivation for this? So there have been all kinds of new, exciting things emerging in condensed matter physics connected with topological materials in the last few years, as many of you know. And this is one example. So in fact, let me show you a picture. So if we have a topological insulator, then we put a layer of superconductor, ordinary superconductor on top of it, and then we apply a magnetic field, so we have a vortex lattice. It's predicted that there will be a Majorana mode localized at the core of each vortex. And then in general, there can be tunneling processes, so these Majorana modes can tunnel from lattice site to lattice site, and there will also be some interactions induced ultimately from ordinary Coulomb interactions, possibly with screening. Also, because we're in a superconductor, it's conceivable the effective interactions might be attractive rather than repulsive. So this model is most naturally studied in 2 dimensions, and in fact, we're working on that right now. But as a warm-up, we studied the 1-dimensional case, which might also be experimentally realized if you had a very thin strip of superconductor so that the vortex lattice was just 1-dimensional. Another attractive feature of this model is, well, there's an extra symmetry present when the hopping term is 0, namely gamma j goes to -1 to the j gamma j. And this symmetry is actually present when the chemical potential of the topological insulator is tuned to the Dirac point of the surface states. And this means, in principle, you might be able to tune to very strong coupling experimentally in this model. So it's of interest to study the phase diagram for arbitrary coupling strength and possibly also for both signs, since it's not clear if the effective interaction might be attractive or repulsive. So I'm going to focus mainly on positive G here, because there's a connection with supersymmetry in that case. Although negative G is also very interesting, and if I have a bit of time at the end, I might say a few words about negative G case. Confusingly, the positive G case turns out to correspond to attractive interactions because of some factors of I. So, so whether or not attractive interactions occur would depend on whether being on top of a superconductor means we effectively have attractive interactions. So let me start by talking about the weak coupling phase diagram using field theory and normalization group methods. Okay, so it's trivial to diagonalize a non-interacting model. We just Fourier transform, and even though the gammas are Hermitian, when we Fourier transform, actually they're not Hermitian, but gamma of -k is gamma of k dagger. So the Hamiltonian can be written this way. So basically, this looks like an ordinary model of ordinary complex fermions. The only hint that we're dealing with Majorana fermions is that the wave vectors only run over positive values between 0 and pi. So if we look at the low energy states, they occur near wave vector 0 and pi. So if we have weak coupling, we can start by weakly perturbing around the non-interacting theory. So the only important effects will occur at low energies. So basically, we only keep Fourier modes near 0 or pi. And these correspond to right and left movers. I've tried to normalize them in a conventional high energy way. So the non-interacting Hamiltonian just looks like non-interacting Hamiltonian in one dimension for Majorana fermions with right and left movers. Now you might ask, well, why isn't there a mass term? Well, there's actually a symmetry that forbids a mass term. A mass term would couple gamma right to gamma left, but this is forbidden actually by translation symmetry, which is going to play a very important role in this story. So translation symmetry, as we see, actually changes the sign of gamma left but not gamma right. So that forbids the mass term. So it's quite well known that a non-interacting Majorana fermion model actually corresponds to the low energy physics of the quantum Ising model in one dimension at the critical point. And there is a very strong connection with the Ising model, which I'll be talking about. Okay, so, well, straightforward enough to analyze the effects of interactions. We just make this substitution into the lattice Hamiltonian, write down the lowest dimension operator which can occur, and rather annoyingly or surprisingly, perhaps, the lowest dimension operator we can write down actually has a very high dimension because we have to have two derivatives because the square of gamma right or gamma left is just a constant. So this is the lowest dimension operator. This already distinguishes this model from the similar models like this you can write down that involve ordinary complex fermions, not real fermions. So this is a dimension 4 operator, so it's highly irrelevant. And that tells us that actually this interaction won't have any effect if the coupling constant is small enough. So if anything interesting happens because of interactions, it will only happen above some critical coupling. So therefore, we expect that this non-interacting massless Majorana phase should be the actual, describe the low energy physics of the interacting model, at least up to some critical couplings of both potentially positive and negative sign. Okay, so now having said a few words about weak coupling, let me now say a few words about strong coupling. So another unusual feature of this model is it's not actually very obvious what happens at strong coupling. And that's unlike the complex fermion version of the model. So if you write down a model of, say the Hubbard model with, say, on-site interactions and fermions with spin, ordinary complex fermions with spin, well, the strong coupling limit is quite easy to solve. Or if you write down the spinless fermion model with nearest neighbor interactions, it's also quite easy to solve the strong coupling limit. But the strong coupling limit of this model isn't very obvious, actually. You can actually map it onto a spin model, but it's a rather non-trivial spin model called the model for anisotropic next neighbor Ising model. And there's some connection to the 8-state Potts model, but it's not a very trivial model to solve, actually. So, but we'd like to get some intuition about what might happen to strong coupling. This could guide us towards understanding possible phase transitions. So I'm going to cheat a little bit, and I want to argue that translation symmetry is going to be spontaneously broken at strong coupling. So let me consider what would happen just for fun if I break the translational symmetry by hand. Because I want to get a model where we can actually solve it easily and get some intuition. So let's suppose that we have an alternating interaction term. So depending on whether it starts at an even or odd site, we have a coupling G1 or G2, and maybe also, for convenience, alternating hopping term. So to get a model we can easily solve, we could set G2 to 0, so we only have every second interaction term, and let's also set the hopping terms to 0 for the moment. So now finally we have a model we can easily solve. So how do we solve it? Well, we can combine pairs of neighboring Majorana fermions to make, we usually call these Dirac fermions, this Hermitian, not non-Hermitian ordinary fermion operators. If you only have G1, this is very convenient because this nearest neighbor product is just twice the occupation number minus 1, so it's plus or minus 1. And the Hamiltonian just takes this simple form. You see, by the way, why positive G corresponds to attractive interactions now, because an I squared comes in. We actually get a minus sign here. So, okay, finally we have a model we can solve. It just describes basically spinless fermions with nearest neighbor interactions. For positive G, we'll get a so-called ferromagnetic state where all sites will be filled or empty. Important thing to realize here is we can't control the chemical potential. So the number density will automatically adjust to minimize the energy. So for positive G, which is attractive interactions, we're either going to get a completely empty or completely filled band. On the other hand, for negative G, we'll get a charge density wave with a particle sitting in every second lattice site. So we see that we actually have quite a bit of broken symmetry here. So I've broken translational symmetry by hand in order to combine Majoranas to make Diracs. Now I apparently get a further symmetry because, well, for positive G, I'm either going to have empty or filled states, and for negative G, I'm breaking translational symmetry again because I'll have a charge density wave where the fermions sit in either even or odd Dirac sites, if you like. Of course, if instead I said G1 to 0, then I can do exactly the same thing, except that now I'll be combining my Majoranas to make Diracs shifted over by 1. So these are some pictures that we find convenient to try to understand what's going on here. So the dots represent the original lattice sites. And when I put a big circle on a link, what I'm saying is I'm combining these two Majoranas to make an ordinary Dirac fermion. I can either do it this way or this way. And if I'm in the positive G regime, I can either have all of these levels filled or all of these levels empty. So if G1 is positive, then I'm going to get these two ground states. If G2 is positive and G1 is 0, I'll get these two ground states. So potentially I've got 4 ground states lurking around here. Now, what happens if I turn on T? Well, let's first of all consider what happens if I only have T1. So T1 actually is just a chemical potential term. And it will actually either favor the filled band or the empty band. So this will actually, if I turn on both T1 and G1, I'm either going to pick one or the other of these two states. But if these states are occurring because of spontaneous symmetry breaking when T is non-zero, depending on the sign of T, I'm either going to favor, say, the empty or, let's say I turn on a sign of T that favors empty bands. So I would get, if I get a spontaneously broken translational symmetry, the two ground states naively would be the second and fourth picture here. So I combine pairs of Majoranas to make Diracs either this way or that way. And once I do it, I get an empty band because if I have attractive interactions, which is positive G. If I have repulsive interactions, I'll get a charge density wave state. There's actually a particle hole symmetry present when T is 0, which is this. This actually relates positive negative G, which is also interesting. So if I take the case where T1 equals T2 and G1 equals G2, then as I was saying, if spontaneous symmetry breaking occurs, this is sort of the cartoon picture of what might happen. I can combine Majoranas to make Diracs two different ways, then the Diracs do what they want to do in a relatively simple kind of way. Right, so I get these two ground states. So notice I've broken translational symmetry. I only have invariance under translation by 2 sites if this is actually what happens. Okay, so we could write the full Hamiltonian in terms of these Dirac fermions, but it's rather complicated. So the hopping term actually is a combination of, in terms of Dirac fermions, a hopping term, a pairing term, and a chemical potential term. And the interactions involve, well, the nice term I showed you, but also they involve rather complicated interactions, which involve 3 sites and combinations of hopping and pairing terms that depend on whether the intermediate site is filled or empty. So rather complicated Hamiltonian. This is the Hamiltonian which my colleagues had to study using numerical methods. Of course, particle number is not conserved as we expect once we include all the terms in the interaction. So particle number, of course, is conserved mod 2 because these terms only change number of fermions in steps of 2. So therefore, I can define a fermion parity operator, just the total number of fermions present, which can be written in terms of the Majoranas this way. This will be plus or minus 1. So I can classify states by fermion numbered. I'll always consider an even number of Majorana sites for simplicity. Okay, so as we go to large G, it might be natural to expect a transition into these broken symmetry states. These states we expect to be gapped. And once we break the symmetry, then we can actually have a mass term. So we might expect to go into a massive gapped phase. And then the nature is, what might be the nature of this question is, what is the nature of this phase transition? And it's actually quite natural to expect that it might correspond to the tricritical Ising model. This is actually the unique candidate critical theory that has precisely one relevant operator allowed by symmetry, and I'll get to that in a moment. So it's a C equals 7/10 conformal field theory, whereas the free massless Majorana corresponding to the Ising model is C equals 1/2 conformal field theory. Actually, as we eventually realized, a lot of what we're doing is sort of following up on a very nice paper by Castor, Martinek, and Shankar from 1989, who actually referenced an earlier paper by Akulov and Volkov. Interestingly, this model at the critical point and also on one side of the critical point actually exhibits supersymmetry, as these people pointed out. And it's somewhat surprising in a way, because we started with a model that only has fermions, and supersymmetry is supposed to link fermions and bosons. So as Castor et al. Suggested, well, if you took a supersymmetric model, integrated out the bosons, and wrote down the effective fermion model, it would actually have this form. So perhaps that's a reason you might expect you might get a supersymmetric model occurring here. And it's well established that the tricritical Ising model is supersymmetric. So this is the phase diagram we actually expect then for positive G. So for weak enough coupling, interactions are irrelevant. We're in this gapless Majorana mode corresponding to the Ising phase. At strong enough coupling, we go into this phase with broken translational symmetry. And there's a critical point which corresponds to the tricritical Ising model. I should mention that the broken symmetry that occurs here is actually not the Z2 symmetry of the Ising model. It's something that's called Kramer's Wanier duality symmetry, as Castor et al. Pointed out clearly. So this Kramer's Wanier symmetry is actually a symmetry that interchanges the high temperature and low temperature phases in the Ising model, or in the one-dimensional quantum Ising model, it interchanges the ordered and disordered phases. There's actually a duality symmetry between ordered and disordered phases. In terms of the Majorana theory, this corresponds to the mass term. So if the mass term has a positive sign, it corresponds to the ordered phase. If the mass term has a negative sign, it corresponds to the disordered phase. If the mass term is 0, you're at the critical point in between them. So this is, if you just think about the classical, you think about the classical Ising model or a quantum version of the Ising model, where you can see the tricritical behavior. So one nice example is a spin 1 Ising chain. So we had a so-called, so these are spin 1s. We had a crystal field term. So depending on the sign of D, this either favors SZ equals 0 or SZ equals plus or minus 1. If D is large and negative, SZ is plus or minus 1. This corresponds to the Ising model. If D is positive, SZ can be 0. And as you vary H, the transverse field, there's a phase transition from a disordered phase at large H, which corresponds to high temperature in the classical model, to an ordered phase at small h. And as you go along in transition, it's second order for a while, but then eventually it becomes first order. And the tricritical point is where you go from second order to first order. And the Kramer's Wanier symmetry is a symmetry that sort of exists along the transition line. It's a symmetry between the ordered and disordered phases. And so that's the Z2 symmetry, which corresponds to translation symmetry in this Majorana fermion model. And the actual Ising symmetry doesn't actually show up here at all. If I introduce, the only way I could introduce Ising spin variables here would be to make a so-called Jordan-Wigner transformation. And this is non-local. So the Ising spin variables are non-local in the Majorana fermions and don't actually appear at all in the description. So so we can think of this line here. Critical line is, transition line is corresponding to this line in the Majorana fermion model. If I break the translational symmetry by making T1 and T2 different, I'm moving off this line. But if T1 equals T2, I have this Kramers-Wanier symmetry. It's actually exact in this model, and I'm moving along this line. So that's actually a nice feature of this model. Kramers-Wanier symmetry is not just an emergent symmetry on the transition line. It's an exact symmetry when T1 equals T2 in this model. So yeah, another very important paper by Steve Schenker was in 1985, which argued that this model is supersymmetric. And it's the Navier-Schwarz sector that occurs here, as I said, because the Ising order parameter is actually non-local. So if we ask what are the operators that occur in the tricritical Ising model, well, if we just look at the chiral operators, which we combine together to make the actual physical operators, well, there's basically 4 of them. Apart from the identity, epsilon is called the, well, it'll be combined together to make the ordinary energy operator. So the boson field epsilon is the energy operator in the Ising model. And then we have 2 other, epsilon prime is sometimes called, I guess, the subdominant energy operator. And we actually have 3 of them, and these are their dimensions. So, and a very important thing is how these models transform out of the Kramers-Wanier Z2 symmetry. So we expect the energy operator to be odd because, as I said, if you go to the ordered or disordered phases, you actually add a mass term, and that actually, in the Ising model, that just corresponds to this energy operator. So this is odd under Kramers-Wanier symmetry, but epsilon prime is actually even, and that means even if the Kramers-Wanier symmetry is exact as it is in our model, this will be allowed by symmetry, and this other one is actually odd. There's also some fermions that occur. So these have conformal spin. This one has conformal spin 1/2 because 3/5 minus 1/10 is 1/2. And this one actually has conformal spin 3/2 because it's 3/2 minus 0, which is a half integer. So we have 2 sets of fermions and actually 3 bosons occurring in the Navier-Schwarz sector, which is the physical sector for the model we're considering. So we can actually combine some of these fields together to make a superfield. So now I'm describing a sort of a Ginzburg-Landau description of the model. It's a bit hand-waving and heuristic, but it captures a lot of the important features. So we can construct a superfield using, so we use the energy density in epsilon prime and the conformal spin 1/2 fermion operators. And the Ginzburg-Landau Lagrangian density is just the usual supersymmetric one with a superpotential W, which is actually cubic. So it actually turns out that we can only get odd powers of 5 for symmetry reasons. Yep.
What does d bar mean?
Oh, I'm just trying to copy notation. I must confess, I haven't done supersymmetry in 30 years, so actually I was reading Bagger and Vest on the airplane as I came here, but I believe that's the usual notation. It's 1, n equals 1, yeah. Okay. All right, no bar. Okay, good. Thank you. But there are theta rights and theta lefts. Okay, but no bar. All right. Okay. Okay, so important point I already mentioned is that the only relevant operator allowed by symmetry at the tricritical Ising point is actually epsilon prime. And because epsilon prime is actually this final component of the superfield, and this again goes back to Castor et al., it follows that this is actually a supersymmetric perturbation. And at a sort of Ginzburg-Landau level, we can just add this to the superpotential. So now the scalar potential takes this form. And if G is less than Gc, the minimum is at phi equals 0, and the ground state energy is positive, which means supersymmetry is spontaneously broken. On the other hand, second derivative of W is 0, and this is what couples to the fermion, so this means that the fermion is massless. So this just describes the massless Majorana phase, and we see that we can interpret the Majorana in the Ising phase as being the Goldstino connected with broken supersymmetry. On the other hand, if G is less than Gc, the minimum occurs, sorry, if G is bigger than Gc, I mean, the minimum occurs at non-zero phi, and now we've actually broken the Z2 symmetry, so we've spontaneously broken this Kramers-Wanier symmetry. That's the other part of the phase diagram, but now the fermion is actually massive. So this describes the first order transition line. So establishing this tricritical Ising point, just justifying this scenario and showing this is actually what happens, turned out to be extremely challenging. And for reasons we really don't understand, This transition occurs at incredibly large coupling, about 250. I have no idea why it was so large. So this non-interacting phase is incredibly robust for positive G, up to 250. On the other hand, for negative G, there's a transition at minus 0.3. So it's incredibly asymmetric between positive and negative G. Of course, if there's any hope of ever seeing this in an experiment, we better find some other Hamiltonian where this transition moves down to weaker coupling, which we've been actually considering. One of the reasons this created numerical difficulties was, well, of course, at the critical point, the correlation length diverges. So you want to sort of move away from the critical point and get into a region where the correlation length is kind of manageable. But if you go on the larger G side, all the way up to infinity, as far as we can tell, the correlation length is probably still bigger than 1,000. So this created huge numerical problems, but remarkably, we were actually able to verify that this is what was going on. So we did it actually using the finite size spectrum. So of course, the value of C is 1/2 for the Ising model, 7/10 for tricritical, and then we have some fractions xn, which are scaling dimensions of operators. So we considered both periodic and anti-periodic boundary conditions in space. And we could also look at states that were either even or odd under fermion parity. So we basically calculated the first few states in the spectrum with either periodic or anti-periodic boundary conditions and even or odd fermion parity. So if you take anti-periodic boundary conditions, then you actually have modular invariance because the path integral is for fermions. So in that case, the spectrum just corresponds to the set of operators, local operators that occur. So for the Ising model, these are the operators that occur. We have the identity operator, the cross term is the fermion operator, and x epsilon is the energy operator. For the tricritical Ising model, we get this set of, this is the partition function, and again, this corresponds to the set of operators I mentioned. If you take periodic boundary conditions, you get a quite different spectrum. So for the Ising model, it involves actually the sigma is the order parameter, which doesn't occur as a physical operator. It's in the Raman sectors. So you actually get this conformal tower squared. The factor of 2, by the way, means an exact degeneracy between fermion and boson states that occurs for periodic boundary conditions, not anti-periodic. For anti-periodic, we can read off which are bosons and fermions that correspond to the physical operators. And for the tricritical Ising, we get actually there's a order parameter and there's a subdominant order parameter, and both of these occur. So once we figured out that these are the partition functions we expect from conformal field theory with periodic or anti-periodic boundary conditions, we can predict the 10 minutes left, thank you. The energies of the first few states in the spectrum, and we can also identify the fermion parity. So we looked at these. We also looked at C from entanglement entropy. So here we're actually convenient to set G equals 1 and take T towards 0. So strong coupling is a small t. So we see that C is sort of locked in at 1/2 until we get down to extremely small coupling. And then it seems to be shooting up to something else. But this sort of starts to show you the difficulties with the numerics. It's hard to see what's happening here. It was also a bit challenging here. But here we looked at a particular ratio of energies. So odd even is the fermion parity. A here means everything's anti-symmetric. Boundary conditions, and 0 just means the lowest energy state in the even or odd fermion parity. And here we look at the first excited state with even fermion parity. So this is a convenient ratio to look at. So for the Ising model, it has value 1/2, and for the tricritical Ising, it has value 7/2, which is conveniently very different. And so as we vary through a range of extremely small t, we see it approaching 3/2 for some range of t around 0.002. Or if we go to a much larger t, we see it approaching the Ising model. In between is kind of a no man's land where we can't get to large enough systems to see what's happening. So if we go to the critical t, which seems to be tricritical, we can actually look at 4 of these ratios and compare them to conformal field theory predictions. And actually, all 4 of them agree with very good accuracy for this value of G over T. So that convinced us this wasn't some kind of dumb luck, and we really were seeing this tricritical transition. I probably should speed up here. We also could look at a correlation function, and a fermion correlation function, and we expect a slope of 1 in the Ising model and 1.4 in the tricritical, which we also see. So what about experimental signatures? Well, one thing we could imagine is doing scanning tunneling microscopy into this superconductor. This would directly measure the fermion correlation function exponents, and we expect it, so we can look at how the current depends on the voltage. So we expect linear behavior in the Ising phase and 7/5 exponent in the tricritical Ising phase. More interesting question, which we're still sort of scratching our heads about, is, well, what happens if we go into the broken symmetry phase? This is also supposed to be supersymmetric. So it's not going to be exactly supersymmetric because there are irrelevant operators that break supersymmetry, but the only relevant operator is a supersymmetric one, the one I mentioned. So therefore, we expect some sort of emergent supersymmetry in the gapped phase with broken Z2 symmetry just slightly above the critical point. So, well, this implies, for example, that, well, the fermion and boson excitation should have the same energy. So if we tunnel in a single electron or tunnel in a Cooper pair or do some sort of photon-induced transition, which actually measures the gap to the lowest energy fermion or boson, we should measure the same gap. But how should we think about this gap phase? And we're still sort of scratching our heads about this. And what really are the signatures of supersymmetry in the gap phase? Well, as I mentioned, the gap phase has unbroken supersymmetry, but it has broken Z2 symmetry. And this is our cartoon picture of what this looks like. So we have two broken symmetry phases where we combine Majoranas to make Diracs either this way or that way. So there's going to be a soliton connecting these things. We see that the soliton is going to have an unpaired Majorana mode. So the basic excitation then are basically these solitons. And actually, with appropriate boundary conditions, you're only going to have even number of solitons. So if you take two solitons, then you're going to have two Majorana modes. If you combine two Majorana modes, you can make a Dirac mode. And therefore, you have a fermion level that can be filled or empty. So the boson and fermion correspond to this Dirac level being filled or empty. And the exact supersymmetry is actually looks rather boring because it just says that, well, you've got these two solitons very far apart. You combine a pair of them, soliton, anti-soliton pair. You can make a fermion or boson depending on whether the resulting Dirac mode is filled or empty. And according to supersymmetry, these should have exactly the same energy. But what's a little frustrating about this is that apparently there are no bound states. And this goes back to an argument by Zamolodchikov and also by Lattice, Musardo, and Carty. And because there are no bound states, it's a little bit hard to see the supersymmetry. Because on average, the soliton and anti-soliton are going to be very far apart. And even if you didn't have supersymmetry, if you had some sort of solitons that had a Majorana mode localized at them, and you can easily write down models that have that property and which are not supersymmetric, then we expect the interaction between these Majorana modes to be exponentially decaying with distance. So if on average they're very far apart, which they ought to be in a large system, even if there was no supersymmetry, you'd probably only expect a kind of exponentially small splitting of the energy of the boson and fermion. So if anybody has some suggestions what a clearer signature of supersymmetry might be in this ordered Z2 broken gap phase, I'd love to hear about it. Here, I guess I'm just combining what I just said. So we can combine Majoranas to make Diracs. It should be an exact degeneracy of the filled or empty state because of supersymmetry. But so what? That's pretty boring because even if there was no supersymmetry, the interaction is exponentially small. This probably implies something about the S matrix when you scatter the soliton and asoliton off each other, so some constraints from supersymmetry. But what we're trying to understand is what kind of experiments might actually be able to really see the supersymmetry here. So I gather supersymmetry may not be seen at CERN, so we're hoping maybe it will be seen in condensed matter physics. And this is something along these lines might be one of the possibilities, but we need to understand better how it might be observable here. And the fact that they're not forming bound states makes this difficult. Okay, so to wrap up, this is the full phase diagram. As a function, I've only talked about positive G actually. So this is 250. So this Ising phase is incredibly robust on the positive G side. Transition into this gapped state, which is actually supersymmetric, tricritical Ising point. Don't have time to talk about negative G, but actually there's two transitions. This one occurs at minus 0.3. So this is plus 250, this is minus 0.3, not to scale. There's another transition at minus 3. This transition is actually not Lorentz invariant, it's a so-called Lifshitz transition, the velocity vanishes. This is another interesting Lorentz invariant transition. And this is the other kind of gapped phase that you might expect based on my hand-waving arguments. So if G is negative, this is where you get the charge density wave. And the charge density wave is actually robust against turning on a small hopping term, because it's like having a ferromagnet or an antiferromagnet and turning on a magnetic field. So if you have a ferromagnet, you turn on a magnetic field, it instantly prefers spin up or spin down. But if you have an antiferromagnet, you turn on a magnetic field, it doesn't actually favor one of the two states, because it's up, down, or down, up, and a small field doesn't actually pick one or the other. So for that reason, we actually have fourfold degeneracy here, because there's two ways of combining Majoranas to make Diracs, and then once we have the Diracs, we can go filled, empty, or empty, filled, empty, filled. So we have fourfold degeneracy. There's actually, as I mentioned, infinite coupling is actually equal with opposite signs, so there's another transition occurring in equal infinite coupling. So altogether, there are actually 4 transitions in this model, this very innocuous-looking model, which only had 1 parameter in it. And one of them is Tricritical Ising supersymmetry. And if you want to read more about it, we've got a couple of papers in this, and we're still thinking about these things. So happy birthday to Nati, and thanks for your attention.
So this is not a question, but I have 2 comments about relation to other things that perhaps some people did not notice the relation. First of all, your Z2 Kramer-Venier symmetry, it seems to me that it's an R symmetry. And that really brings nice memories from the early 80s when R symmetry was very important. The other thing is that these particles that you talked about at the end are precisely the object that Gayotto discussed in the first talk,
which I missed
this morning, where he had a duality and he had domain walls that duality changes.
Interesting.
You mentioned the question of whether these models are integrable.
Yes.
So I think it's known from the work of Zamolodchik of around 91 that the tricritical flow from the tricritical point to the Ising point, it's an integrable model.
Yes, sure. What I meant was whether this lattice model itself is integrable. And as far as I know, it isn't.
Yeah, just a comment. I'm not sure it's known to you, but just in the continuum formulation of the Yukawa theory with the Majorana fermion and the real scalar, you can check the emergent supersymmetry in 4 minus epsilon expansion. Actually, our last paper with John B. Tarnopolsky and Fay did it to 2 loops, and you can shoot and check that in 2 dimensions. You match on pretty well to the tricritical Ising model. So it's actually works order by order in epsilon expansion.
I see. Nice.
Did you have? Any last questions? Okay, if not, let's thank Ian again.